So hello and welcome everybody to this year's Quantum Materials public lecture, From Rust to Riches. My name is Helena and I am the Quantum Materials Outreach Officer here in the Department of Physics, and it gives me great pleasure to welcome you all here this evening. Now it gives me great pleasure to introduce our speaker for today. So with us today we have Professor Paolo Radaelli. Professor Radaelli is the leader of the Quantum Materials Research Group here at Oxford, and also holds the position of Dr. Lee's Professor of Experimental Philosophy at the Clarendon Laboratory in the department, as well as being a professorial fellow at Wadham College. His main research interests is the study of transition metal oxides, which display novel and interesting physical phenomena. So things such as high temperature superconductivity, colossal magneto-resistance, or multiferroics behaviour, all looking towards the potential of using these in new device applications. And today he is going to be sharing with us some information about his recent exciting results published in Nature earlier this month, and talk a little bit about how Rust might actually hold the solution to problems currently faced in computing technology. So I will hand over to you now, Paolo. Thank you very much.
Thank you very much, Helena, for the great introduction, and thank you all for attending this lecture. I'm going to share my screen. So that's the title, you've already seen it. And as Helena said, the title the talk will describe the results that we recently, published in the journal Nature, called Antiferromagnetic Half-Skyrmions and Bimerons at Room Temperature. I posted in the chat two links, one to the paper itself, which you may find somewhat indigestible, at least until you listen to the lecture, and then one to a kind of short description on the Oxford Science blog. So my aim today may seem a bit strange to focus a public lecture on a single paper, but these days this is how science advances, through this peer-reviewed publication. So it's gonna be interesting to talk about that and to try and explain to you the meaning of terms that may seem a bit esoteric, such as antiferromagnetic, half-skyrmions, and bimerons. I hope everybody knows what room temperature is. So so part one, the heat is on, both metaphorically and literally. This is a toaster in a thermal imaging camera. I'll show quite a lot of thermal imaging in this talk. And why is the heat on? Well, it looks like everybody who's not an astrophysicist or a particle physicist and is not working on COVID-19 somehow is working on problems related to climate change. And this is only right that we should do that. I mean, this is my poster first slide, and this is there to illustrate both the beauty of our planet and the disruptive power that can generate when mistreated. And this is another one, beautiful image of three hurricanes. These are Harvey, Irma, and Maria, the three big hurricanes in 2017 that landed on the east coast of the United States and on the in the Gulf of Mexico and wreaked so much havoc then. So everybody's trying to work on ways to prevent anthropogenic climate change or global warming to make these things worse. And everybody's trying different approaches. I mean, there are people working on fusion energy to produce cleaner forms of energy. Other people are working on battery technology to be able to store energy more efficiently, and others on transmitting energy more efficiently, for example, with superconductors. But one aspect of this game that is often overlooked is the problem of energy consumption in information and communication technology, which is growing exponentially. This is a paper in Nature. So this is the projected energy consumption in information and communication technology over the next decade. And you see here the growth up to the projected value of 20%, 21% of the total energy production. And most of it, the green bit here, is related to data centers. Okay, so it's really the core business of generating and data, storing data, and processing data that consumes a lot of energy. And of course, this is a big share of the electricity production globally. And why is this so much energy involved in that? Fundamentally, because the silicon technology that we use for computing is inefficient. And just how inefficient it is shown here in the next video, in which I will show some nice thermal imaging camera shots. Okay, so this is, let's see if I can start this video to illustrate the difference in energy efficiency between biological computing, which hopefully should be in the head of this person. You can see here the temperature scale is 35 degrees. Let me just stop it for a second and go back to show you what we were seeing here. Okay, so the scale goes from 17.4 Celsius to 35 Celsius, and this is the temperature scale of a person, as you know. Okay, now we turn up the scale to 71 Celsius and look at the back of a computer. Okay, 71.7 Celsius, and this is the back. And the stuff you see glowing here are all the inners of the computer. In fact, this is the graphic part. The graphic part. Sorry, I somehow accidentally restarted the video. Okay, we're back there. Right, so this is the graphic card of the computer, and we can see if we zoom into that. Actually, this is the back of the computer. You see the fans that cool the computer and the glow behind those fans, which are necessary to keep the temperature down. Again, the scale is 71.7 Celsius. If we then stop the fans and look at the microprocessor, which is actually doing the calculation, we see something extremely interesting. That's the microprocessor in the next section. It's idle at the moment, but if we turn the computation on, you see this glowing bright yellow, and the scale here is 100 Celsius. In fact, these microprocessors are designed never to exceed about 100 Celsius, so they actually stop computing or slow down the clock speed until they reach about 100 Celsius. Okay, so that's that. So translated into numbers, okay, we can compare once again the energy efficiency of silicon-based computing to that of biological computing in the human brain. So this is the IBM Subnet. It's one of the most powerful supercomputers in the world. Its speed is calculated to be 148 petaflop. So a petaflop is a million billion floating points operation per second, 10 to the 15 floating point operation per second. And its memory is about 2.7 petabytes. So a petabyte is 1,000 terabytes. So the hard disk I'm running this talk from, which is here, you should be able to see that, is 2 terabytes. Okay, so that's a coherent memory, not the storage memory. So the one that is immediately accessible. However, this computer requires 13 megawatts of power to run. That is the small power station, and its space occupies about 2 basketball courts and more than 2 meters high. So it's very energy hungry. Its purpose is to design nuclear weapons, to study astronomical objects, to solve energy problems, solve human genome problems, and solve the problem of climate change. Now compare that with the human brain. The human brain has a speed, estimated speed by some metrics. It's not easy to translate the human brain into floating points operations. It's about 40 petaflops, so not that different. The memory is quite similar, but the power is only 12 watts. So it's a millionth of the Summit, okay? And the space is occupied is only about 1.5 liters, okay? So it's about 1 million times more efficient, and the space is related to that, because whereas a silicon-based computer has to dissipate a lot of power, so it needs a lot of cooling. You know, that chip I showed you before is only about 1/10 of a millimeter, so I can't pile them up, otherwise I would melt the whole thing. The human brain is so energy efficient that essentially can run all packed up in 3 dimensions in 1.5 liters. Okay, so that really tells a powerful story. We have more than 1 million times to gain just to go to the human brain, and that's not a limit. The ultimate physical limit is another 1,000 times more efficient. Okay, so it overall is 1 billion times more efficient that we can gain. Right? If you compare with battery technology, for example, there's so much work on battery technologies, but batteries are only about a factor of 4 from the ultimate physical limit. The computing technology is 1 billion times. Okay? So there's a huge prize to be claimed by researching these things. But are we going to change silicon technology with something that is more efficient at computing rather than producing heat anytime soon? I'm afraid not. And this is shown in the next video. So this video here shows a computer chip as we zoom in and look at how this computer operates. Okay, so this is a digital camera. And zooming into the computer, this is not to the chip, not even one of the latest generation chips. And soon it will switch to electron microscopy to show really the innards of it. I should be able to stop this. Okay, so we are about 6 microns here. Let me stop here for a second. And by comparison, this is an electron micrograph of a human hair. That's about 50 microns in diameter. Okay, what we are seeing here at the same scale is not even the computing brain of the chip. These are only the interconnects. Okay, to see the actual brain, we have to zoom in further. So we can let's see if I can restart this video. Yeah. So we zoom in further and further, and this is a micron, and the size of the transistors is about that. Okay, so if you were to be able to zoom in, you will see something like this. Okay, so this these objects, if I can go back to that, these objects, this is 800 nanometers. So a nanometer is a billionth of a meter, and the smallest feature that can be designed in this chip is about 3 nanometers, which is about 10 atoms. Okay, so the technology is fantastic, and it's this very technology that prevents progressing to a completely different technology, perhaps much more efficient. Okay, because there are billions invested in this technology. A single fabrication facility called the fab costs about $10 billion. Okay, and all this investment worldwide is not going to be dissipated by these companies, which, by the way, make a lot of money out of these things, unless the technology is so superior that it's really worthwhile doing so. So this is the dilemma. We know there is a price of 1 billion times, but we don't really know how to claim it. So there are many approaches. Oh, by the way, let's remember where this all started from. Okay, this is the first transistor, or actually a replica of it, built in 1947 by Bell Labs. You know, you recognize Bardeen, John Bardeen, and Schottky in that picture. And it was about the size of a small objects here, but you know, macroscopic, really like your fist. And it feels like with many technology, we are actually at that stage, not at the stage of the 3 nanometers, right? So we have a long way to go. So what approaches are there that we could use to claim that huge price? Okay, so the second part is called bits, bubbles, and beyond. And it's a nice picture of a bursting bubble, and it's there for a reason that I'll show you in a second. So there are many different technologies to become more energy efficient. This is one that is very much in the popular press. This is the Google Sycamore, the famous quantum computing chip that claimed quantum supremacy about a year ago. Okay? So quantum computing is a completely different technology, which is based on a different computing principle, and it's known to be able to solve certain classes of problem a lot faster and a lot more efficiently in terms of energy than classical computing. So that's one approach that people are following. Certainly nothing that could replace silicon even in the medium term. Okay? Another approach is to use quantum materials. And this is the quantum materials series. So it's only right to talk about quantum materials. So quantum materials are a class of materials that have fundamentally different properties at the atomic level. And they can be used for both quantum, or they could be used for both quantum and classical computation. Okay? Both approaches, classical meaning bit-based computing rather than qubit as in quantum computing. And another approach is that of looking back at all technologies that perhaps stalled at some point, but maybe we could make a breakthrough and kind of push them over the boundary and make it really closer to be able to claim the price. So this is one such technology. This is called a bubble memory. You can see it's a chip produced by Intel in 1982. And this particular chip has a capacity of about 1 megabit. Okay, so you see a quarter there. So an object like this today would hold several gigabytes. Okay, but this is 1 megabit. It was a big deal in 1982, very promising technology, which, however, was completely superseded when silicon-based memories like DRAMs and flash onto the market. So how did this work? If you look microscopically with a microscope at it, you would see a lot of these bubbles. This is why it's called a bubble memory. So these bubbles actually are magnetic bubbles. So when you see dark green, you see, it means that the compasses are pointing towards us. And we see light green, the compasses are pointing away from us. And these form bubbles, which are relatively small, and they can be moved around. And the memory worked by that principle, by moving these bubbles around. So they were moved actually by a series of coils that produces magnetic field, which is not very energy efficient at all. Another reason why this technology didn't work is that these bubbles are actually not that small. So if you see again the human hair that I showed before, you know, that's about 50 microns, and it's the same scale as the bar scale there. And you could see here that you know, these bubbles are nowhere near the kind of circuit limits that I showed you before, right? So they basically stalled. But why not trying to make these bubbles even smaller? Okay, or find ways of making them more efficient to move about. And the reason is that when you make magnetic things small, they tend to pop like a soap bubble. And this was really the problem that they encountered at that stage. However, a lot of progress was made. And this is a video that shows you the old type of bubbles and the new type of bubbles that have been researched more recently. So this is the kind of old type of bubbles. You see these stripy things, so ignore the dark stripes, which are defect in the materials, but the other stripes are magnetic stripes up and downs, and you see bubbles forming here when you apply a magnetic field. This is kind of the old types. And this is, let me stop here for a sec, if I can. Oops. Okay, no, I can't, sorry, I've got to restart that. Okay, so let me start here, stop here. Okay, so this is the old type of technology. And then the new type of technology is here. And let me start here. This was from a paper published in 2015 by Axel Hoffman of the Argon Group. And you see much smaller bubbles. Oops, much smaller bubbles here. Let me see if I can go back to that place. Okay, I'm going to just start here. Okay, these bubbles are about less than a micron. Okay, much smaller. And you can blow them through this tube. The tube is about 20 microns long. You can blow them using a small electric field. So much more efficient way to produce them. Okay? So we want to go down very small, and we want to go down in such a way that they don't burst. And how do we do that? Okay, so that's the next slide. Part 3. We need to use the power of twisting. Twisting makes things stable, as the old rope makers knew very, very well. You know, if you twist the strands of a rope, you make a rope very stable. It never gets undone. But if you don't twist them, the rope gets undone. So twisting things makes things stable. How do we twist a magnet? Let's please suspend the disbelief for a moment, that whether we can twist the magnet or not. And let's explore a little bit how the right twist can make things stable. So let me stop the share for a second. And I prepare a demonstration. So this is a braid, okay, which I braided myself, okay, using basically shoelaces of different colors. Okay, this is a braid. It has knots at the end. So this is one knot, and that's the other knot. Okay, and it's braided in such a way that you know, in the ordinary way. So it's very stable. I can pull it as much as I want. Okay, so I hope you agree that this cannot be undone other than by untying the knots or by cutting it. Okay, so here it is. This is the braid. This is another braid that I made. Okay, you can see it's exactly the same. All right, the braiding is the same. The colors are different, but the braiding is the same. I can show you all the parts of the braid. Okay, and the knots are the same. So the knots are genuine knots. Okay, so I'm going to show you something. Okay, so this is it. 1, 2, 3. Okay, completely undone. Can somebody write in the chat? I know there's some pretty clever people in this audience. Can you write how I did it? This is the knots are still there, right? I didn't undo the knots. Magic trick. Yes, indeed. You can do it yourself. It's very easy. Okay, I'll tell you. I'll tell you how it's done. Okay, so basically you tie the knots like this. Okay, and then what you do, you start braiding it from one end. Okay, you start braiding it from this end up to about half, and the other half will braid itself in the opposite way. So when you show it, yeah, exactly. Somebody has understood it. So you braid it halfway, and the other way, half will be braided the opposite way. And then when you pull it, the braid and the anti-braid will annihilate. Okay, so braiding things makes things stable, but you have to be a right braid. Okay, so you have to be twisted the right way. Okay, so that's just kind of magic trick. Good. So that's that. Okay, so how do we braid a magnet? So stop suspension of disbelief. That's for real. Okay, so let me just share the screen again. Okay, so let me see what I can do. Okay, so what I want to tell you is that in order to twist a magnet like a braid, what you need to do is to do a frozen vortex. So by frozen vortex, I don't mean something like this. Okay, I don't mean something cold. I mean something stationary. So let's see if I can run this little video. So this is an ordinary vortex. You can create again in your kitchen sink. It's a beautiful structure. It's like a hurricane. This is why I showed a hurricane at the beginning. And this vortex however, is the dynamic vortex. It only exists because there's energy that feeds it. Okay, so if you stop it, you get. Let's see if I can stop it. Okay, you get something that you may call frozen vortex. It's frozen fill. But in fact, what actually the magnet does is that if you plot the velocity field and you convert it to magnetic field. So imagine you've got a compass at each point, and that points in the direction of the flow. That's your magnetic vortex. Okay? So we want to create something like this. And this in a way is similar to what Axel Hoffman has done in these objects. Actually are not simple bubbles, they're what are known as fermions. So they are in a way twisted vortices of this kind, although slightly more complicated. Okay, so this is what we're trying to do. How do we act? But the problem is, how do we create these things? We cannot go around with compasses at a nanometer scale. You have to exploit the power of nature creating things out of nothing in a way. Okay, so inspiration came from many different directions, and one direction is ice. So you see here ice that is cracked. The cracking of ice comes about for a very simple reason. When you cool ice, it contracts and then it cracks because of the stresses. But at the microscopic level, at the atomic level, these cracks start from atomic-like defects that arise when the ice actually freezes from water. And interestingly, water cannot have cracks of any kind, either atomic or macroscopic, whereas ice can. So there is a change of phase, a change of state of matter that produces the atomic defects, which will now turn into cracks. And this what we call a phase transition that enables these things to happen. And the description of these defects is related to the description of the braid through a field of mathematics called topology, which is kind of really encompassing on many different scales and including the theory of defects in solids such as ice. Okay, another source of inspiration for us, actually the main source of inspiration, was far away into the cosmos. And in fact, we were talking about cosmic strings. What's a cosmic string? So if you are a Star Trek fan, you know a cosmic string is bad. This is a USS Enterprise being trapped by a cosmic string, and poor Captain Picard trying to disentangle from it. So it's a stuff of science fiction, but there is actually something much more profound and actually physical about cosmic strings, although we don't know yet whether they actually exist or not. They were first proposed, I believe, by Tom Kibble, which was a physicist at Imperial College, which considered the problem of the universe just nanoseconds after the Big Bang, cooling from a state of very high temperature to a state of slightly lower temperature and undergoing, again, a phase transition, a change of state in which the nature of vacuum changed. So his model was actually very simple. There have been many, many more development of cosmic string theory since. Please don't ask me about it because it's not my field. But the very simple mathematics that Kibble developed, in fact, turns out to be applicable to many other things in nature. And in fact, this other guy called Wojciech Zurek, about a decade later, understood that it could be applied to ordinary matter, in particular, rather ordinary matter. He applied it to liquid helium or superfluid helium, which is kind of cold, very cold liquid. But it can apply to many other things, possibly including a magnet. And this was the idea, and this is where it came from. And this is the challenge that we set ourselves. Can we create the equivalent of a cosmic string in a magnet? So let's focus on important things about cosmic strings or objects like this. They don't exist in a particular state of matter. When you change temperature, they could exist, and they come about out of nothing in some way. Okay, and they're also very, very stable. So people, astronomers, think that we may be able to observe them at some point in the future if our instrumentation is powerful enough. Okay, so this is our inspiration, but can you really do it in a magnet? And it has to be a special type of magnet, very exotic perhaps? Well, it turns out the solution was quite uncannily one of the humblest types of materials, rust. Okay, so part 4, humble rust. So what is rust? Well, it's many things, but one of the main components of rust, here's another beautiful piece of imagery of rust on a sculpture. The main component of rust is iron oxide, okay, Fe2O3, also known as hematite. It's called hematite because it's red. Hema in Greek means red. So iron oxide is actually a beautiful mineral. These are crystals of hematite in a different form, and is actually a magnet, but the magnets of a very special kind. So let's zoom in at the atomic scale and show you how this magnet works, right? So because it's quite different from the normal magnetic materials that you put on the fridge or something. So okay, so if you zoom in at the atomic level, you see the atoms here, or at least a picture of them. The yellow golden things are iron atoms, and the red things are oxygen atoms. Okay, and they form a honeycomb lattice. Okay, so this is just one slice of it, 1 atom thick. Okay, so each of these atoms has associated with it a magnetic moment, a microscopic compass. Okay, atomic scale compass, which we call magnetic moment, but in short, we tend to call it spin, although spin and magnetic moments are 2 different things, but we call it spin. So they're all pointing in the same direction. So each honeycomb layer points in the same direction. This direction is in the plane of the honeycomb, so it's not up, but it's in the plane of the honeycomb, at least at room temperature. And it doesn't really matter in which direction it is, provided that all the compasses are pointing in the same direction. Okay, so there's not a lot of energy difference in pointing in different directions, although there is a little bit, as we'll see in a second. Okay, so this is 1 atomic layer thick of hematite. Okay, so I'll represent these compasses with arrows for simplicity. Okay, so that's the whole crystal structure of hematite, also known as alpha Fe2O3. There are different phases of Fe2O3, by the way, but this is kind of mineralogy beyond the scope of this talk. Okay, so this is the whole crystal structure, but if I isolate these slices, you see these honeycomb slices with all arrows pointing in one direction. If I go to the next slice, the arrows point in the opposite direction. Okay, and the next slice again in the first direction. Okay, they're all pointing north, south, north, south. So this means it's not an ordinary magnet. If you put an ordinary magnet next to it, it wouldn't be attracted at all. It turns out it's slightly attracted, but for a different reason. Okay, okay, so this is the room temperature structure of hematite, magnetic structure of hematite. Okay, so it's an antiferromagnet, anti because the spins are antiparallel in this fashion. Okay, now if I cool just below room temperature, it's a very moderate temperature of your freezer, minus 15 Celsius, the magnetic structure changes. Okay, so it's still ordered in the same way, but the layers now point up or down, not in the planes of the honeycomb, but in the plane perpendicular to the honeycomb. Okay, so this transition is known as a Morin transition. Francis Morin was in Bell Labs in 1950, and when he studied these things, it's change of state of matter. So it's analogous in a somehow distant way to the cooling of the universe and the freezing of water into ice. All these different things are phase transition. And also the other thing you will notice is if you, let's go back to that, okay? So this thing can point in any direction. So it can form a vortex if you are able to. Whereas when it points up or down, it cannot form a vortex. It's either up or down. It cannot be in any intermediate direction. So this phase transition is the one that we identified. Actually, we did think about it. It's not by chance that we discovered it. That could form vortices, that could form tiny magnetic particles that are braided in the way the braids I showed you before, okay? So that's that, okay? So how do we make our special rust? We use this machine. This machine is called a PLD, pulse laser deposition system, okay? So this is how it works, okay? So you have, if you look into that light, that's a laser light, and it shine on this white thing. In this case, it wouldn't be white, it would be red. This is hematite, essentially compacted rust, no more than that. And it produces a plume. You see this beautiful plume of colors. This is actually evaporated rust, okay? And this evaporated rust wafts onto this object on top, okay, here, which is the substrate, which is red here, it shows red, because it's been deposited onto it. This is heated as well. And so this is how we grow our rust. And it turns out it grows perfectly aligned because the substrate provides an atomic scale template of it. So it's perfectly aligned with all the layers or honeycombs pointing up, so pointing out of this film. So it turns out the substrate is sapphire, because the sapphire has the same crystal structure as hematite. Now, you may be worried that you don't want to have an expensive sapphire in your computers. Actually, sapphire is not very expensive, but we now have methods of taking this very thin layer, is about 30 nanometers thin of sapphire, of hematite, and peel it off. And then we can reuse the sapphire as many times as we want, if you're worried about the cost. We also put a layer of platinum, very, very thin, like 1 nanometer platinum. You know, your hard disk is full of platinum, so you don't worry about cost there. It's an infinitesimal cost compared to everything else. But the platinum has a specific purpose, which I'll explain to you, and is for the future, not for what we've done now. Okay, how do we study it? With a special light. This is the diamond synchrotron, in a beautiful light, by the way. And we're using the X-rays produced by the diamond light source about 15 miles south of Oxford, closer to my home actually than it is to Oxford, to study the vortices, these tiny braids that we hope to create in hematites. So this is another beautiful picture of diamond. And we use an instrument called it's a bit of a mouthful, an X-ray photo electron emission microscope using soft X-rays. Okay, let me explain these words. Okay, X-rays, you know, X-rays, it's you know, CAT scans and things like this. Soft X-rays, why soft? Well, they have very low energies, like they are not as penetrating as the ordinary one for X-ray radiography, and they are precisely that energy because we tune the energy to a resonance of iron. So we make iron atoms resonate as a guitar string. And when they resonate this way, they are very sensitive to magnetism. This is why we use soft X-rays, okay? So photoelectron emission microscopes, that's a very complicated machine, looks more or less like this. I don't want to explain that. I unfortunately cannot take you to Diamond because of COVID, etc. So I built my own little X-beam machine. Let me stop share. And my friend Laurent Chapon, who's probably online, will forgive me because his machine cost millions. My machine, I found a way to make it very, very cheap. So that's my beam, okay? And this is another component. I'll show you how it works. Okay, so I turn on the flashlight, okay? And I shine it through these glasses, okay? So what I get here is a source of polarized light. These are my sailing glasses, are highly polarizing. Okay? So I create a source of polarized light, which will enable me to demonstrate how the X-beam works. And my sample is going to be that, you know, again, you can do it at home. It's a normal calculator. I can type some numbers here. You can see them, hopefully. Anything, I can type anything. You can see this. And I hope you can see in any orientation. All right, I can turn it around, I can see them. Okay, now let me share a screen again. Okay, so I made a little video because I could do the demonstration live, but I would have to turn the light off. It didn't work quite well. So I'm going to run it. Okay, so that's the calculator under my beam light that I built. Okay, so I have it like this, and then I turn it. Okay, I turn it, and what I see is nothing. Okay, and then I turn it again in the other way, 90 degrees the other way. And again, I see nothing. Yeah? So if I turn it, so I could have turned the glasses rather than the calculator. And in both cases, I would have seen the same thing. So if they are not oriented parallel to each other, but if I turn it 180 degrees upside down, I get the same image. So I cannot tell whether I'm up or down. In fact, here I'm sensitive. This is a liquid crystal display, as many of you would have guessed. And I'm sensitive to the orientation of the molecule. Actually, it's a molecular level probe that I'm using here, in spite of this simplicity. Now, the actual X-beam, there's a difference in that, first of all, it uses X-rays, and secondly, instead of measuring reflected light, it measures electrons, photo-emitted electrons. Okay, so the electrons that are emitted via the photoelectric effect are measured in an electron microscope, giving me the possibility of having resolutions down to about 20 nanometers. Right? Very, very high resolution. Okay, so by this light, what did we see? We put this film at room temperature or slightly below room temperature in our X-beam at diamond, and surprise, it's always holding your breath. The first time, and this is the first experiment we did in 2017, this is what we saw. Okay, so you see the scale bar here is 2 nanometers. The diameter of this is about 6 nanometers. Remember that the picture from Hoffman, the channel was about 20 nanometers, micrometers, okay, 2 micrometer here, and the diameter is 6 micrometers. So I said nanometers, micrometers. So we saw this very intricate pattern, and the glasses in that case were oriented in such a way that we were sensitive to the different orientations of the spins in the plane. Okay, so this was actually made into a cover of Nature Materials two years ago, and the colors are not random. They were chosen because my students did something really, really clever. Okay, so they turned the sample in the same way that I turned the calculator before, and they got different images. And these different images, so they take it, here's your glasses, you turn the sample, or you turn the glasses, but we turn the sample, it turns out, we rotated the sample underneath. And all these different patterns are taken in the same position with different orientation, and enables you to reconstruct the direction of the spins on the surface. The spins are predominantly in the surface. This is room temperature, remember. So the spins are in the honeycomb, okay, that is on the surface of the film. Okay, so this is the beautiful image that we reconstructed, and if we zoom in, we see vortices. It was magic. The first time we saw it, it was fantastic. So you see here this square, the white square, is really a vortex, and the little line show you the direction of the spins, and they circulate like a vortex. And here it's interesting. The black one is different. Okay, so the white one is an ordinary, not known as elliptical vortex, really a hurricane. And the other one in the circulation is opposite. It's called an anti-vortex. So this is the two pictures, like a hurricane on top and the anti-vortex. And these are like the two braids, the braid and the anti-braid. They can annihilate each other in principle. Okay. So actually we didn't see, so we call it Meron. Meron means that the spins at the center actually go out of plane, like really in the eye of the storm, like the eye of the hurricane, where the flow is downwards. In this case it's upwards, but it doesn't matter. Okay, so actually we didn't see that in the first experiment. We only saw the vortex. And the other thing we did not see in the first experiment, that was a big disappointment, was that we changed the temperature, we saw nothing. Okay, so these things got there by chance. We couldn't create the kind of Big Bang equivalent by cooling. So we were hoping that when we cool down below this transition where all the spin point up, that would be like the beginning of the universe. Not quite, but almost. So in any case, that phase cannot support vortices. And then we warm back up and we see vortices appear. But this didn't happen, and we couldn't figure out why. So it was a good paper, but we couldn't understand why we didn't get all the way. And it took us a couple of years to get to that point. to where we understood what was going on. And a lot of experiments and failures. So, you know, we fail. And then we now know how lucky we were the first time. So the first time we just got these things by chance. Now we know why, and we know how to make them. So we made some beautiful new samples. And this is the second experiment. 2019, and then later we wrote a paper at the beginning of last year and got accepted in Nature and published this year. Okay, so right, so okay, first of all, we actually got clever. We did different experiments with different orientation of the polarizer, okay, of the X-ray polarizer. So this time we also looked at the polarizer in such a way that it was predominantly sensitive to the cores, okay, so the spins that pointed out of the honeycomb, right, that in the honeycomb. So we have two modes, one that looks at the vortices or the vorticity, and one that looks at the cores, the outer plane part of the vortex, the eyes of the storms, okay? So we looked first at low temperature, and this time the low temperature phase, the just immediately post-Big Bang phase, or the water phase if you want ice and water, is the first thing we looked at. And this is what it looked like, so low temperature phase. And the blue bits here, colored in blue, is this outer phase spin phase, so the one that cannot have vortices. And the yellow one is the in-plane phase, and you can immediately see what's happening. So most of it is blue, but some places is blue up and some places is blue down, okay? And in going from blue to blue, so from up to down, it has to go to in the plane, so we see yellow, okay? So if you look at the other orientation of the sunglasses, so the in-plane orientation, you see all these beautiful colors, because you only see colors when they have spins in plane, essentially. So this is the same thing, but in the low temperature phase. No vortices here. So these stripes are very beautiful, but they're not very useful. They're very big. So this bar line is 1 micron. You don't want things that big. You want things really tiny, okay? All right, so now we warm up and hold your breath, right? Or we did. Yeah? So this is the warming up. So we're starting from -70 and warm, okay? You see this borders grow, and then what you're left is are dots. Okay? These are your bubbles. Okay? Then we cool back down from there, cool the bubbles, and then they become big, and you're back on the stripes. This is magic. Right? We never in our dream think that we would see this so clear. Okay? So these bubbles are really, really tiny. So this scale bar here is 1 micron. Okay, so these sizes, these tiny bubbles, about 50 nanometers. Remember the experiment of Hoffman, this bar was 20 microns, and these things were about 1 micron. Okay, so these things were as big as this bar. Okay, now these are much, much smaller. Also, you notice they come in pairs, and this is very important. Okay, so now we turn our sunglasses the other way, and we look at what the spins elsewhere are doing, not just the vortices. And this is again beautiful. Pictures that we can see by rotating the sample and reconstructing all these. So by the way, the colors are marked, so they are constructed in such a way that essentially red means north or south, green means north, east or southwest, and the blue means south, east or northwest. Okay, so again, we cannot tell. In the same way I showed the calculator, if we flip up upside down, we can't tell what we're looking at, and the same thing is here. Okay, so the color and this little stripes that I show here, these are actually the spins. They don't have an arrow because we can't tell up from down, as I explained many times already. Okay, so zoom in some of these features. These are the ordinary, or they call them block merons. They're ordinary, the white ones here, they are ordinary hurricane type merons. So they know they have a core now because we've seen the core. So they spins out the plane, they point up. And they're called block merons because they essentially outside the core, they behave like a normal hurricane. Now, this type is a different type. It looks like, if you look at the nail meron, it looks like a hedgehog. Okay, so it's a different type, but still topologically, so in this mathematical theory, it's still very much the same object. And this other type, the yellow type, is the antimerons, which is the same for both block and the nail. Okay, and the block and nail are two pioneers of magnetism, by the way. Okay, so lots of different objects that we can see, a lot of zoology, and then the other thing we see is the pairs. Okay, what we call bimerons. So the interesting things about these are the most interesting technologically if we can standardize them, because they can exist in a uniform background. They don't need to have all these colors around. They can exist on their own, and they can be very small. Okay. The only problem is that we don't know whether they are like my braid, the first braid I show, that are highly stable, or they can collide and evaporate. That they are paired with the antiparticle or paired with a particle that is not the antiparticle. Okay? So that's still a little bit of a mystery, but we are still quite convinced that we can create the right type of bimerons, the Q equals to 1, we know Q equals to 1 bimeron, and that we can create lots and lots of them by learning how this process works. Anyway, this idea of going through a phase transition, creating these objects worked fantastically well. Okay, so I'm finished. Whence from here? That's my last couple of slides. So where do we go from here? It's like could be the beginning of a big journey, or could be a dead end. We don't know, but this is where we think we're going to go, and this is a kind of nice artist impression built by Paolo G, who is our collaborator, first author of the paper, and his father and other people. So this is kind of artist impression, obviously. So this strip is meant to be this bubble strips, the equivalent, the modern equivalent of this bubble strip, in which we want to create lots and lots of these things and move them with tiny currents. And we know this should be possible. You remember I told you that we use platinum, a tiny coating of platinum. So if we inject a tiny amount of current in the platinum, we should be able to move these things super fast and super efficiently with tiny amount of energies. Now, can we build the transistors based on this? I don't know. I haven't thought about how to do it, but this is already really quite good, and we're very happy. So this is the next thing we want to do. Also, we can tune very well the temperature. So, you know, it's awkward to cool down to -15, but we can change that very easily by just chemical composition, tiny changes in the hematite. And the other thing we want to be able to do is to again tune this temperature and create lots of these things and learn how we can create a very large population of these things without having them annihilate. So that's the really tricky thing. Okay. So I think I would like to leave plenty of time for questions. Yeah, so my last slide is an acknowledgement of all the, there are many more people that work on this project, but I just want to mention a few. So diamond light source, the institution, of course, diamond light source was crucial. And this is Francesco Macrozzi at the beamline. He's the wizard of the beamline, and so the equivalent of the sunglasses, but, you know, multi-million pound sunglasses. He was the one that made it work. People who made the samples are crucial here. So these special rust that we made, so various people here. So here, this guy here is Changbom Eon, who made the first sample out in Wisconsin. These two people, Venki Venkatasan, here in my arrow showing him. He's the guy that invented the PLD technique, by the way, which now is widespread use, and his collaborator Ariando. And this Hariom Jani here is in the center. He's the first author. He's also in Singapore, very enthusiastic. And some of my students here, Jahao, JC Lin, and Jack Harrison, and many other people contributed to that. So I want to really thank them from the bottom of my heart, because this is really immense fun. And I want to thank you for your attention. And I will stop here.
Wonderful. Thank you so much, Paolo. That was such a fascinating and brilliant talk. I learned so much from that myself. It's amazing the things that are actually going on inside of Rust. Who knew? Okay, brilliant. So I think we'll move on to some questions now. Yep. So there's a couple at the top. So the first one, what are these bubbles made of? So that was when we were talking about the bubble. Okay.
So these bubbles, essentially, they're all the same material, except that what makes the bubble is that the spins, or the microscopic atomic scale compasses, they point in one direction, and the surrounding materials, they point in a different direction. This is what the bubbles are made of, right? And it turns out in ordinary magnetic materials, in some situation, it is advantageous for these bubbles to form. And this is basically due to the interaction that normal magnets experience. At that scale will make them form bubbles.
Okay. Brilliant. And then we've got someone else asking, what did p-flops mean?
Yeah, petaflop is peta. It's the prefix for 10 to the 15. So it's a million billion, so it's a million billion flops, which is floating points operations per second. Okay, a million billion floating points mean operations, mathematical operation that have a point. Okay, so not integers. Okay, so like things like 1.2375 10 to the minus 25. This is a floating point number.
Brilliant. Thanks for explaining that. So someone asking, when you did the demonstration with the sunglasses and the calculator, when you say you saw nothing as you were rotating it, how come the screen was blue instead of being
That's a good question. I have no idea. Is the way that the light is reflected? Is the way the light is reflected by the layers which is actually a complicated stack of layers in the liquid crystal. But it's a very good question. So I will encourage you to investigate. But we didn't see the numbers. That's the important thing.
Yes, it was just that blank blue screen, wasn't it? Yeah. Okay, so next question. One of the properties of oxides is that it is magnetic and can move magnetic bits around in the oxide as well as in magnets. Yep. Why do these bits we talk about are really tiny? So why is 10 nanometers about the target figure? Yeah.
So the reason, okay, so you could do a lot of things at different scales. So if you take a hard disk, a modern hard disk, a normal high density hard disk, actually several hundred nanometers are the bits. Okay, they are static bits, you cannot move them around, but you can write and rewrite them. There's a new technology actually came on the market this year called heat-assisted magnetic recording, where you can make them even smaller and even denser. And remember, every time you stream a film on your TV, that's recorded somewhere on a hard disk. It's still not silicon memory, it's a hard disk. Okay, so 10 nanometers is a good target because we know that silicon technology is at that scale. So there's if you can make things at that scale, you can make things that are compatible or probably competitive with silicon, because it has that kind of density. Now that doesn't mean that you can use merons to do a meron transistor. At least we don't know how to do it yet, but at least you've got the right length scale to be able to attempt that.
Brilliant, that makes sense. Okay, next question. So considering that the modern computational revolution was driven by consumer applications and use for the convenience amongst other functionality made available by modern day computing, how much do you think that consumers would actually be able to take advantage of such powerful computers?
Yeah, okay, that's a very good question. I think it's not only a question of power. So obviously, if you have something that is as efficient as the human brain, which we know it's possible because the human brain, after all, is a biological machine, what would you do with that? Okay, so how would you even program something that is as powerful as the human brain? These are all questions that are important. But so far, what I'm actually, even if you make computers that are as powerful as present-day computers, but use a millionth of the power, you could use a huge number. You can, all the data center, essentially the electricity bill would go to zero if you make them 1 million times more efficient. Also, you can power a lot of things with batteries that you wouldn't be able to do it, and the batteries will last a lot longer. So that's also important. Your mobile, everything is going to be having some kind of computer in it, and often remote, often in locations where they don't have access to electricity. And if you can have a battery last a month or a year, which you could do. So that's the reason.
Amazing. So there are clear trickle-down benefits for the everyday consumer for this. Amazing. Okay, next question here. What causes the layers of hematite to have opposite spins to make an antiferromagnet at room temperature when within the lattices they point in the same direction?
That's a very, very good question. So essentially the spins, okay, the atomic scale compasses in all materials, including ordinary iron or any magnets that you have, these things interact with each other very strongly, much more strongly than ordinary magnets. Okay, this interaction, which is due to quantum mechanics, this is why all magnets in a way are quantum materials. This interaction is incredibly strong. Now, sometimes this interaction want to make them align, parallel to each other, north-north, south-south, and some other times want to make them anti-parallel. It turns out in hematite, because of the crystal structure, the interaction in the plane, in the honeycomb plane, wants to make all parallel, and in the next layer down, anti-parallel. Mm-hmm. Okay? So if you take another oxide, very common oxide, chromium oxide, Cr2O3, same crystal structure, in the honeycomb there will be anti-parallel. Okay, so it changes depending on the material. They're all different. It's the quantum mechanical interactions between these magnetic moments that make them align or anti-align. They can also form spirals, rotate, and various other things, but the more common are the ordinary ferromagnets and the ordinary antiferromagnets, as I showed you.
Brilliant, fantastic answer. Okay, the next question. So they're asking, some quantum computing architectures are making the most of CMOS processors. Are there possible opportunities to use your work to enhance this approach? So do you know what that's talking about there?
Yeah. So, okay, so actually the computer chip that I showed you before, the Sycamore computer, it doesn't use CMOS, it uses actually superconducting qubits made of aluminum and aluminum oxides as barriers. So it's a different technology. There are approaches, as you correctly say, that uses CMOS, although there isn't any CMOS type quantum computer that has reached quantum supremacy or even close to quantum supremacy. We could very well do that. So perhaps a question, okay, so certainly having silicon CMOS compatibility, it's very, very important. You don't want to have a technology, especially if you want to get into the market rather than, you know, which is the logical thing to do. You don't want to supplant silicon, you want to use silicon and something else. You want to be CMOS compatible. CMOS means complementary oxide semiconductor, metal oxide semiconductor. So essentially what I call silicon technology is more properly called CMOS. So we think we can make these things on silicon, and the reason why we know is that we can peel them off. We already done it, and they have all their properties. And then when you peel them off, you can put them back on silicon. So we think we can make it CMOS compatible. This is really key.
Okay, brilliant. And I think we'll probably do a couple more questions. So the next one is asking, do you have to keep the hematite on the phase boundary to keep the vortices stable?
No. The further from the phase boundary, the more they're stable.
Great, brilliant answer. Feel free to look through and see if there are any in particular that you want to answer as well for the final questions.
Well, lots of questions actually.
Yes, there are a lot.
So I will just go through quickly. Floating points already explained is things with a dot and an exponent, so kind of big numbers. Comparing with human brain is really just a game. We don't know whether we can, this is not, it's like Asimov's positronic computing. We don't know. We can't even make, hedgehog brain, let alone a human brain. So yeah, it just is a token of comparison about the power of biological computation. Bubbles related to Cooper pairs, not in the sense, although perhaps there is some similarity as far as the way they do pair up, but they pair up in real space, whereas Cooper pairs pair up in a different way. Yes, spin wave can propagate through hematite. We actually did some beautiful simulation. When these bimerons are like the fake braid that they make, so they can annihilate, it's beautiful. We do these movies, they are simulation of hematite, but they're very accurate. What happens, they collapse and they burst because they annihilate each other. And then you get beautiful spin waves propagating from them. And they propagate very fast. They propagate at 40 kilometers per second, which is very, very fast for these materials. Yeah, the stripes tend to be pinned most of the time, but they can. So if they're not always in the same place. You can move them quite easily, actually. Initially we have tried with magnetic field that they can move that, but we hope to be able to move them by tiny currents. The bubbles are not charged carriers; they are just magnetic moments.
Any other final questions?
The system that have similar effects. Can you irradiate it? Yeah, we have tried to do ion implantation. So far, it didn't work. It made it brain dead. But we're hoping still.
Okay. Do you want to pick one final question?
I don't know, just at random.
Oh, yes. One that looks interesting.
It seems that the bubbles crop up at random. It would be possible to set them in a desired pattern, i.e. address them. Yes. So we have loads of ideas. One idea, if you want the bubbles to be fixed in a pattern, okay, you can actually, the idea of ion implantation. So you bombard them with ion, you create location for the bubbles to lock, and then you can make a pattern. That was one of our ideas. So if there are free bubbles, actually, there are lots of implementation. Actually came out of IBM, beautiful work, using things like this kind of free-floating bubbles, and the original implementation had free-floating bubbles, so they didn't have to the bubble memories. So they didn't have to be a particular location. But we want lots of them and very stable. That's what we want.
Okay, excellent. So I think on that note, I think that's about all we've got time for tonight. So thank you again so much.
Thank you all the audience, wonderful audience. Thank you. Bye.
Yes, thank you to the audience as well, and thank you for all of the wonderful questions as well. Sorry we couldn't answer all of them. Thank you everyone, and good night.
Bye.